Okay, welcome back. And today we're going to be looking at some exercises involving vectors. So if you haven't done the exercises yet, check the link in the description below for a worksheet, a PDF that you can go download on my website and try out these exercises first. And then once you've done them, come back here, finish the rest of the video and see how well you did. All right, so let's continue on here. We'll start with question number 1. It says, use a scale drawing of the 4 vectors to the right to find the magnitude and direction of the following. And A is vectors A plus B. Okay, so in order to do this, I am using an online ruler protractor tool here. It's called MB Ruler. And if you're using Windows, you can download this for free. And I'll put a link down in my description there as well. It's pretty useful. So the way this works is right now I've set the scale in pixels. So you'll see right around here, it has a distance, and D is measured in pixels. And then underneath that is alpha, which is measuring the angle, right? So down here I have an angle of 0 degrees, and then here is 90, and here is 180. And then I can pick this up and move this around to draw and measure all of the vectors that we're going to need in today's exercises. So, okay, so for A, I'm going to be measuring vector A plus B. So let's draw out vector A here, and I'm going to measure this in pixels. So something like this, and come back to the origin here, and now I've got a line that is 200 pixels long. So I'm going to use that to represent vector A right there, okay? And I'm also going to draw now vector B. So vector B is going to be measured at 45 degrees at a distance of 125 meters. So let's put that around, just around there. Close enough. Draw that in, and now we've got vector B. Okay, let's remove this for a second. So A plus B, what is that going to look like? Well, we have going to have A, and let's move that over here. And then we've also got vector B right here. And we'll use the chain method or the head to tail method because I'm not a big fan of the parallelogram method, as you know. And now the resultant vector is going to be equal to, it's going to be equal to this right here, where we move from the very beginning at the very tail all the way to the very head right there. So this is going to be our resultant vector that we'll call R, just like that. And now let me bring back the little protractor ruler, and let's measure this resultant vector to see what it actually looks like as far as its value. Okay, so the magnitude looks like it's going to be about 310 meters, and the angle is about 16.1. So let's just write something like that. So it's going to be about 310 meters and an angle of about 16.1 degrees. Okay, so that is the result of this sum. 310 meters and 16.1 degrees. We just literally drew it out and measured it. That's what we're going to do for the rest of these questions here as well. So let's look at B. B is going to be vector B plus vector C. Okay, so let's draw that again. Let's draw vector B. All right, vector B we said is going to be 45 degrees and about 125 meters, something like this. Let me get that. Perfect. Okay, this is vector B. And we're adding to this vector C. So let's get vector C drawn out here. Now vector C is going to be 300 meters and 20 degrees counterclockwise from the y-axis. So that's going to be 90 degrees plus 20 degrees is 110 degrees, right? So about 300 and 110 degrees. So just about here. This is going to be now vector C. Okay, so now we need to add these two together. And remember, addition is commutative, so it doesn't really matter which order you put this in. I'll just grab vector B right here, and I'm going to move it up to the head of vector C like that. And now I'm going to draw the resultant vector. So that's going to look something like this, starting at the very beginning of the chain and going towards the very end of the chain, just like that. So this is going to give me my resultant vector that we will call R, and we can measure this. Okay, so let's bring back our protractor ruler, and let's measure the value of this resultant vector. So it looks like we have a length of about 370 and an angle of about 92 point, well, hard to say, 92.5, about that. So about 370 meters and 92.5, we'll say. Okay, so that's what we've gotten here for part B. Let me select this real quick and just tuck it out of the way so we have more room to draw other vectors, right? Okay, now for part C, we have D minus A, vector D minus vector A. So let's draw out vector D first. And that's going to be something like this. Let's bring back our ruler here. Okay, so vector D is 20 degrees counterclockwise from 180. So that'll be 200 degrees with a length of about 190. Okay, pretty close here. Let's try that. Close enough. Okay, good. So this is going to be vector D. And now we want to subtract A. Now remember, when we do subtraction, what we're actually going to do is add the negative of the vector. So let's draw negative A. Okay, negative A is going to be a vector that is 200 meters in length, but it's going to be now in the opposite direction. Okay, so let's just draw this here. All right, a little finicky. Okay, pretty close. Okay, so this is going to be what we would have for A, and it's now going to be facing to the left because it's going to be negative A. This is the negative A vector. Now we're going to add them together. So we can do that fairly simply. We'll just move this vector over until it is forming a chain with vector D, and now we can draw this resultant vector starting from the very beginning to the very end right there. Beautiful. Okay. And this is going to be vector R, our resultant. And now let's bring back our ruler to measure it. Okay, so we're going to measure this. Let's bring this back all the way to here. And this sum looks like it's going to be about 389 or 390 meters long and an angle of 190 degrees. So 390 meters long and an angle of 190 degrees. There we go. Okay, so let's move this out. And tuck it away over here, just so it's out of the way. And now let's do the final one. Okay, part D here, we're going to have 2 times the vector B plus C minus D. Okay, let's do that. So 2 times b. So 2 times b is going to be 45 degrees. But instead of being 125 meters, it'll be double that, right? So it's going to be 250 meters. 250 meters long here at a 45-degree angle. We're looking at something like this. Beautiful. Okay, so this is vector 2b. Just like that. Okay, so we've got 2b, and we want to add vector c. So let's draw vector c again. Vector c, if you remember, is going to be an angle of 90 plus 20, so that's 110, and a distance of 300 meters, something like this. Perfect. Okay, so this is going to be vector c. And finally, we need to have negative d, okay, negative d. So what we can do is we can just draw vector d, and then we'll put the head on the opposite direction. So we have an angle of 180 plus 20 is going to be 200 degrees, and a length of about 190. So something like this. Oops, sorry, didn't get my straight line. 190. And a vector angle of 200. Something like this. Okay, very good. And now we can draw the arrowhead on this side. So this is going to be the negative d vector. Okay, now we just need to add these 3 vectors all together to get our sum. So let's do that. Well, any order really works. Let's try moving this around first. And we'll put it right there. And then we can take this and move it down a little bit. Something like that. And then we'll take vector c and add it to the chain. Putting it up here. Okay. Now we need to draw our final resultant vector, and that's going to be in green here. That's going to start at the very beginning, go to the very end right here. And yeah, we've got a little bit of overlap, but you're going to still be able to measure it. So let's bring back our protractor, and let's measure this. Okay, so this final result will start at the very beginning and move to the very end. And what do we see? Well, we've got a length of about 589, 588, let's say 586, and an angle of 64.4 degrees. So 586 meters and about 64.4 degrees. And there we have it. Okay, so we have successfully drawn out a scale drawing for each of these 4 vector sums, and then we measured the angle and magnitude of each of those resultant vectors. So hopefully you would have gotten something similar to this. Now notice that there is a good deal of experimental error when we make these drawings. There's error when we draw the initial vector line. There's additional error when we move them around to try and connect them head to tail and make this long chain. Then there's an additional error when we draw the resultant vector, and then there is an additional error when we measure the resultant vector. So there's quite a lot of error here. So if you're a little bit off on the measurements, don't fret, that's perfectly normal. This is all within experimental error. Okay, let's go on to question number 2. Okay, for question number 2, it says you decide to go for a run. You start out running due south for 2 kilometers. After that, you turn left and run due east for another 5 kilometers. At this point, you stop and wonder, how far away are you from home and what direction home is? Using a scale diagram, find the magnitude of your displacement and the direction of home in degrees away from north. Okay, so this is similar to what we just did using a scale diagram, but this time we're not given pictures. We have to reconstruct the vectors from these words. So let's do that. You start out running due south for 2 kilometers. Okay, let me just draw a little compass rose here. Okay, here's the idea. This is north facing up. So we're going to draw a little map. Okay, so you start running due south for 2 kilometers. Okay, let's do that. Let me bring back my little ruler. And let's say that we're running south, yes, for 2 kilometers. And again, I'll say 200 pixels represents 2 kilometers. Okay, let's do that. So 200 pixels around here, and we should be pretty good. Oh, let me draw a straight line if I can. There we go. Okay, so this is going to be 2.0 kilometers due south. Okay, perfect. And let me move this a little bit so we have some more room. Move that up just a little bit. Okay, so that's our first vector. And now at this point, we turn left and run due east for another 5 kilometers. So let us measure that. And I'm just going to start right here where we were. Okay, so now we are going to do 5 kilometers. So I'm going to say that's 500 pixels. And we're running due east. Just like this. Perfect. Okay, so we run due east for 5.0 kilometers. So far, so good. Now, we want to find the magnitude of the displacement, so that's going to be the length of the resultant vector, and the direction of home in degrees away from north. Okay, so let's do the magnitude of the displacement first. Well, let's switch to green here, and let's see if we can't measure this, right? So we're going to, well, there's different ways to do it. Let's start at the very beginning, and then let's go to the very end here, and let's make our resultant vector, just like that. Okay, so this is our resultant vector R, and we want to measure its magnitude. So we're a little bit off the screen there, so let's just measure it from this end. It's going to be the same length. So that is 543, so that should be about 5.4 kilometers. That's what we're getting here. So we're getting 5.4 kilometers for the measurement of this length, of this magnitude. Now it says that we want to have a direction now from north. So imagine you're standing here now, and north is going to be straight up over here. And so what we want to know is degrees away from north. We want to know what this angle is right over there, okay? And so we should be able to measure that angle. We can just get our little protractor back over here. And again, we'll just measure and see what this angle is here. So that's about 158 degrees. But we have to remember, this 158 degrees is from here all the way to here. That's not what we want. We want to subtract this 90-degree angle here. So we're going to subtract 90 degrees, and we should get an answer of about 68 degrees. Okay, so that's going to be our, let's do it in green, our degrees away from north. And this should be our answer then, okay? It's we're now 5.4 kilometers away from home as the bird flies, and we're 68 degrees away from north. So there you go, that's the answer. Now let's look at part B. Part B asks to now find the same magnitude and direction again without using a scale diagram, and it says, note you have a right triangle. Okay, so essentially what we're going to do is we're going to check this magnitude and this angle using a new method without measuring the scale diagram directly. And the key is that this is a right triangle. When we have a right triangle, we are able to start using other tools. In particular, we can use Pythagoras, and we can use trigonometry because we have a right triangle. So the Pythagorean theorem is, of course, a squared plus b squared equals c squared. So if we know that this leg is 2 and this leg is 5, we can calculate the hypotenuse right there. Okay, so in this case, we can say something like the magnitude of r of that resultant squared should be equal to 2.0 kilometers squared plus 5.0 kilometers squared, right? So let's do this calculation. Let's just find the magnitude here of this vector, and that's going to be the 2.0 kilometers squared plus 5.0 kilometers squared, and then we take the square root of all of that. And what is that? Well, let's use our calculator. Okay, so we've got 2 squared is 4, plus 5 squared is 25. That gives us 29, and we need the square root of 29, which is going to be 5.39. Look at this. This is going to equal now 5.39 kilometers. And would you look at that? By calculating it directly, we can see we got a pretty decent estimate just by drawing and measuring it out. Okay, so we're halfway there. Now let's get the angle. How can we get the angle? Well, what you're going to notice is that this angle theta, because this is a right triangle and you have some parallel lines here, we can see that this is a similar angle. This is also angle theta. And now we should be able to use some trigonometry to relate theta to these other two sides. And we should know that the tangent of theta is equal to the opposite over the adjacent, right? TOA. And in this case, the opposite is going to be 5.0 kilometers, and the adjacent is 2.0 kilometers. So this is all going to simplify. The kilometers cancel, and we're left with an answer of 2.5. So now theta is going to be the inverse tangent, or arctan, of 2.5. And what is this? Let's use our fancy calculator here. We have a 2.5, and now we need to take the inverse tangent of that, and we get an angle of 68.2 degrees. Would you look at that? 68.2 degrees. That's pretty close to what we measured using our protractor and ruler. So, a good check, and it shows that right triangles rather, are very useful. Because they will allow us to directly calculate vector magnitudes and angles, right? Directions. And this is going to be a key part on what we're learning in our next lesson. So this right triangle is a great introduction to what we'll be doing next. So if you think that this helped you out at all, please give me a like and a sub. It really helps me out. And I'll see you back for the next lesson where we continue learning about how to do a vector arithmetic and build on the foundation that this example here has given us. Thanks a lot, and I'll see you then. Bye-bye.